Now, let's talk about something else. A buffer. What is a buffer solution? So we use a buffer solution when we want a solution that has a very small change when you add acid or base to a solution. So a buffer solution has a very small change when you add acid or base to it. Like the body, the stomach and the like have natural buffers so that the acid base situation in the body does not change that much, such as to kill a person. So that is a buffer solution. Normally we make it by having a mixture of a strong acid and its conjugate base. So not a strong acid, a weak acid and its conjugate base. So a buffer has a weak acid and its conjugate base. So like the Henderson-Hasselbalch equation really can also deal with buffer, because in there we have acid and its conjugate base. Now let's look at how the buffer solution maintains the pH of a system, or only provides a very small change to the pH of a system. So we will use this example. A 1 liter buffer solution contains 0.100 mole of acetic acid and 1.00 mole of sodium acetate. Ka for this for acetic acid is 1.8 times 10 to the power negative 5. So the question is, calculate the new pH. The new pH after adding 0.1 or 0.01 mole of solid sodium hydroxide. So the first thing you think about is, if you add solid sodium hydroxide, all the solid sodium hydroxide is going to dissolve. So the solid sodium hydroxide is going to dissolve and become aqueous. And also one other thing that I need to change in this question, I would say here, instead of 1.00 mole sodium acetate, it should read 0.100. So get rid of this. So this solution contains 0.100 mole of acetic acid and 0.100 mole of sodium acetate. So that's how it should read. It was a mistake there to have 1.00 mole. Alright, so how do you solve this? To solve this problem, first you need to know what is the initial pH before adding the solid sodium hydroxide. So as usual, we are going to use the HH equation naturally. So pH is pKa plus log base divided by acid. But in this case, we know that we know that the concentration of base is equal to concentration of acid, which is 0.1, especially that both are in 1 liter, should be 0.100 more per that 1 liter, because this is the volume these two concentrations are, and here you are given moles instead of concentration, so you have to divide the mole per the volume that you are having. So in the end, we are still going to have for both of them 0.00 molar as their concentration. So because of that, our pH will be equal to pKa, because this one will become 1 and log 1 is equal to 0. So we get rid of this part. And the pKa will be minus log 1.8 times 10 to the power negative 5, which gives us 4.74. So we can say that before adding sodium hydroxide, pH was 4.74. Now, what does the addition of sodium hydroxide mean? So to think about the addition of sodium hydroxide, for example, if you have an acid and you add sodium hydroxide is going to reduce the concentration of acid. So added sodium hydroxide is going especially to reduce the moles of acid. But then if you add sodium hydroxide, the added sodium, because it is a base, hydroxide is going to increase the moles of conjugate base. That's what is going to happen. So because of that, normally we have a table. So the first thing is you are going to have the first table, and this table will be given in more units. And yeah, let me just make some, delete something. So the table is going to be given in more units. So this is the added sodium hydroxide is given as OH minus. This sodium hydroxide, when you add it to acid, the acetic acid, because that's what you are doing, this sodium hydroxide is going to produce, when you add it to acetic acid, it's going to produce some water and a base. So this is a conjugate base that is being produced plus some water. But in this case, you are using more units. You are not using molarity. You are using just more units. So let's say before adding, how much of this did you have? You didn't have anything. So you put 0.00 more. And before adding, as per our question says we had 0.100 more of the acid. And our question also says that before adding we had 0.100 more of the conjugate base. So for now we are not concerned with the water. Now what do we have after adding? So just try to get this one to give myself more space. So after adding, we said that we add 0.010 more of sodium hydroxide. So if we add that amount, all the sodium hydroxide is going to react. Is going to react with the acid. So we are going to still have 0.00 more. Reason: all sodium hydroxide has reacted. So you are not going to have it at equilibrium. But then, what has it reacted with? The sodium hydroxide has reacted with the acetic acid, therefore reducing its moles. And we know how much of sodium hydroxide has reacted. We know that it is 0.01 more that has reacted. So in the end, what we are going to have is minus 0.010 more. Let me give myself more space here. So we are going to have, because we are removing this, minus 0.010 mole. We are removing these moles from sodium hydroxide. We are removing them from this guy here, because sodium hydroxide is reacting with this acid. So we are going to have minus 0.010 mole from the acid. So what do we have here? When added sodium hydroxide is going to increase moles of the conjugate base. So as the added sodium hydroxide decreases the moles of the acid, it is going to add to the moles of the base. So we are going to have here plus 0.010 mole. So after we do this, the final moles so I can get rid of this part. It has accomplished its function. So the final moles, eventually the OH will still be 0.00 mole, but this one, the acid, will be 0.90, because 0.010 has been removed from this. So this minus this will give us 0.90. While the base is going to give us 0.110. So as you can see, we have increased the base and then reduced the acid. So once we do that, we move on to use our Henderson-Hasselbalch equation to give us the final concentration that we want to obtain. So what do? pH. So H equation. pH is equal to pKa plus log base divided by acid. So that will give us a new pH. And our pKa, as we found before, was 4.74. This plus log, the log of 0.110, that is our base, divided by 0.090. Actually, this should not be 90. 0.100 more minus 0.010 should be. This was a mistake, so I need to make a correction on this one. Should not be 90, but it should be 0.090. So this makes more sense. So in that case, if I find myself some space here, the pH will be equal to, let me just do the calculation. 1 divided by 0.09 plus, so it will be 4.74 plus 0.087, which gives us 4.83. So this is based on the assumption that we are still using 1 liter of the solution. So the addition of the OH did not change the volume of the solution. So this is our assumption. Addition of the OH minus did not change volume of solution. So because of that, we can just change the moles to molarity because it's moles per liter. So this is our new pH. So what is the change in pH? Our change in pH is the new pH minus the old pH, which gives us 0.09. 0.09. So this is pretty a small change, indicating that our buffer solution has worked. So when you see a small change in pH, you can easily say, you know what, this small change is because we are dealing with a buffer solution. Now, if you want to compare that, if you want to compare with a situation where you don't have a buffer solution, the change will be really, really huge. If you just dissolve 0.01 moles of sodium hydroxide in one liter of water, the change will be huge. So let's say, for comparison, dissolve 0.010 more solid sodium hydroxide in water and see what happens. What you are going to have is that the pOH of your solution will be given by minus log 0.010. That is which is 2. Now we have an equation that we have not discussed much, but pH plus pOH is equal to 14. So in this case, our pH will be equal to 14 minus 2, which is 12. So if you look at that, just dissolving 0.01 mole of solid sodium hydroxide gives a pH of 12. And you can see that when you dissolve it in a buffer, the change was just 0.09, which means the buffer solution really works and is an important solution in life. Now, as we said at the beginning, when dealing with problems like these, you need to ensure that we are assuming that X is small. So always test it. So if I can go back to our problem, our final pH was 4.883. Our final pH was 4.83. But we assumed X is small. So we'll have to find out if X is indeed small. But we know that negative log the concentration of H3O plus is equal to the pH, which is 4.83. This implies that the concentration of this is equal to 10 to the power negative 4.83, which gives a concentration of 1.47 times 10 to the power negative 5 molar. Now, our original acid concentration where we calculated the pH was 0.090 molar. So we'll test our X divided by 0.090 times 100%, which gives us 0.016%. Therefore, our approximation is valid. Let's look at a third example and the last example for this video. In this case, we have a buffer solution, but it is a base buffer solution. The first two solutions were acid buffer solutions. This is a base buffer solution. So calculate the pH of a buffer solution that is 0.50 molar in NH3 and 0.20 molar in NH4Cl. So here it says for ammonia, Kb is 1.76 times 10 to the power 5. So remember, you are given Kb here instead of Ka. So we have been given Kb instead of Ka. So the first thing that you want to do is to find Ka. So solution. First, find Ka. How do you do that? We have an equation. pKa plus pKb is equal to 14. You need to keep this important equation because it will give us the Ka that we want to use the HH equation. Once we do that, we can say pKa is equal to 14 minus pKb, which gives us 14 minus, and the pKb is in parentheses here, minus log, another parenthesis, 1.76 times 10 to the power negative 5, parenthesis, parenthesis. So it gives us 14 in the end, 14 minus 4.75. So our pKa is equal to 9.25. Now once we find pKa, we can come back to our equation. pH is equal to pKa plus log base divided by acid. So in this equation, this one is our base. Ammonia, we know, is a base. This one is our conjugate. Let me just make sure. So this one is our conjugate acid. So if I continue this side, I'll say that pH is equal to the pKa, which is 9.25, plus log the concentration of the base is 0.50. So 0.50, and the concentration of the acid is 0.20. That is the conjugate acid. Now once I do that, I have 9.25 here plus 0.40, which is 9.68. So the pH of a buffer solution that is 0.50 molar in ammonia and 0.20 molar in ammonium chloride is 9.68. So you can see that this buffer solution is actually at a basic pH. But first, you need to find Ka. If you are given Kb, you need to change Kb to Ka, like we have changed here. So this is a very important formula that you can use to do that. Once you do that, you have your pKa. So you are given a conjugate base here, or you are given a base. You take that one as your base in the HH equation, and the conjugate acid will be your acid in the HH equation. So this is how we solve acid-base problems using the HH equation. Thank you.